I think we have our usual people present. We can probably just continue. I think last time at our meeting, it was agreed that Dr. Santilli might make some introductory remarks or follow-up remarks regarding some questions. If we want to proceed with that first, I think that's quite okay. We may also have some desire on people's parts to make some comments or some short discussion on Dr. Sotrik's draft paper from last week. So we could do that also. But of course, we need to leave enough time for Dr. Georgiev to complete the planned presentation. So, Dr. Santilli?
Yes.
I'm sorry, is it the audio not working properly?
Yes, works. But as I understand, firstly, Professor Santilli will answer of the questions or not.
It is entirely up to you, Dr. Page, Dr. Georgiev. I can do it also after the by Dr. I see that Georgiev is ready to deliver his talk, and maybe I can, if you agree, Dr. Page and Dr. Cruz, I can do my very few comments after the Dr. Georgiev presentation. They are mainly physical, as per Dr. Cruz, very important, very sound question indeed. They are strictly physical, and they are connected to the issue, what is the ISO unit? Actually, more precisely and more in line with Dr. Georgiev talk, what is the isotopic element? Because Dr. Georgiev correctly represents everything with isotopic element, which is the right way to do it. I can do it after, and then we can discuss Dr. subject. That's up to you, Dr. Page.
Okay.
Okay.
That's fine.
Yes. Last lecture, we have introduced some sets of with several ISO units, some operations with the elements of this sets. Also, we have introduced isotrigonometric functions and inverse isotrigonometric functions. Today, we will start with isometrics, and after isometrics, we'll introduce isorotation and grid isoreflection. Also, we'll give a definition for isomotion. Suppose that m and n are integers. Also, the element head t is positive. Its inverse is head I. Also, head tj are positive numbers, and their inverse are denoted with head ij. These are the basic ISO units. Then the matrix with the following entires, whose elements will be noted by A11 head T1 and A12 head T2 and so on, A1 and head Tn, and so on, as the elements of m row is AM1 head T1, AM2 head T2, and so on, AMN head Tn. These elements are the following elements. These are the quotient by the real numbers Aij and the corresponding isotopic elements. In other words, the matrix which can be represented in this form will be said isomatrix of order n. Shortly, an isometric matrix will be denoted in this way. The set of all isomatrices of order n will be denoted with this symbol, with head under the letter M. So as a first example, we take for the basic isotopic element head T to be equal to 2, head T1 to be equal to 3, head T2 to be equal to 2. Consider the following real matrix, then its isolift is given with the following matrix. Here the elements are different than the elements of the real matrix. Next example, we'll consider the case when we have 3 rows and 4 columns. For the isotopic element head T, we take to be 2, head T1 to be 1 over 2, head T2 to be 3, head T3 to be 1 over 4, and head T4 to be equal to 2. Then we consider this real matrix. Its isolift is given with this matrix. Again, we see that all elements are different than the elements of the considered real matrix. As first example, we take for the isotopic element head T to be equal to 3 over 2, for head T1 to be equal to 2, head T2 to be equal to 1 over 3, and head T3 to be equal to 1 over 4. If we consider for the real matrix to be this matrix, 3 times 3, then the corresponding isolift is given with this matrix. So if we consider two isomatrices, head A and head B, then we define iso-addition and iso-subtraction in this way. It is similar as in the case of the real matrices. As an example, we take for the isotopic element to be 1 over 9, for the isotopic element head T1 to be equal to 2, head T2 to be equal to 1 over 3, head T3 to be equal to 4, head T4 to be equal to 5, head T5 to be equal to 1 over 2. We consider the following real matrices, which are with 2 rows and 4 columns. Then their isolifts are given with the following isomatrices, and their sum.
Could I ask just one question for clarification?
Yes.
The iso elements that you're talking about, or the iso units that you're talking about here, are do they form a matrix themselves?
Yes. Yes.
If perhaps if you could skip back maybe 2 slides where you define isomatrix, I could understand more clearly.
Yes, yes. Isometric, we can define and generalize the so-called iso distance. Before maybe 2 lectures, I have defined what is iso distance. From here, we can generalize this iso distance as isometric. But yes.
No. My question was just simply the definition of isomatrix. It occurred perhaps two slides ago.
Perhaps I can introduce
this one.
This one, yes. I want to understand.
It's an ordinary matrix. However, with the elements are given by the iso numbers. That's
yes, but the problem I have here, I guess, is that I see in the second row, second column, something labeled 2, 2.
Yes. See, we take.
But you have only.
Yes. Here is a misprint. This is A22 over head T2. With this.
Yes. Okay. So in other words, this T hat is a a row matrix? Is that like a one by, or well, my problem really is the question is the way that these n scalars enter into this matrix. So I cannot write this as a. I would like to see it written as a matrix product. I guess maybe that's what.
So the idea is the following: because N matrix is a generalization of the iso vector. See, the first row we can consider as an iso vector.
Okay.
Yes. The second row corresponds to the other iso vector, and so on. And a row corresponds to this iso vector.
In the sense that there is some underlying iso space.
Yes, in the sense of the iso space. Because an iso vector is an iso matrix with one row and n columns. Then following, as we have defined the iso vector, that real number over the corresponding isotopic elements, we can generalize for iso matrix with n columns and m rows. Okay, or not?
Okay.
Excuse me. In the same way, then we cannot use this definition of matrix like one operator.
Yes, we can use as an matrix of an operator. Yes, but it is early to speak for iso operators, because we have to see how we iso multiply two matrices, iso matrices, then what is the iso determinant and so on. After.
Excuse me, because I am trying to understand, for example, in quantum mechanics, you can write one operator with the states of the system. Then if you get all the states of the system, you can build the operator. But here, if we are multiplying by the inverse element, in this way that you are putting, I don't understand how interpreted the states of the systems. I think that you are using those like rows in the matrix.
Yes.
Then this right, and then you are only taking the transformation of that state with the operator of ISO unit.
Yes.
With ISO unit. Then if I am right, then I have to read the states like a row in the matrix. And what are the meaning of these numbers of rows that we are seeing in this matrix?
But maybe it depends on the state of your system, because here the rows can be 1, 2, and so on. The number of the rows is arbitrary.
Maybe a related question is if I were to use this matrix to operate on a column vector, right? What would be the meaning of the column vector?
So I think that above definitions, if we use not the row as vector, to use the column as vector, as isovector, above definitions will be equivalent. To see as a first column to be this row, this will be the transpose matrix. Okay. And then many of the operations will be the same as in this case.
Perhaps if I am allowed, I can give an example of applications of the question by Dr. Cruz. Again, Dr. Cruz, your question is indeed important. Basically, what you see here, the T's, what we call, we do in practical application in physics, we call them iso-renormalization. In other words, in physics, there is a normalization due to, for instance, to potential interaction, which are very common. And then in hadronic mechanics, we have the new class of renormalization of physical quantity, including iso-renormalization of the mass and other quantity, caused by, this time, non-potential interactions. So think about this road. In the road, this is our set of particles. Here, here there is a mass, ordinary mass in the conventional matrix, the conventional interpretation of quantum mechanics. What you see here is an iso-renormalization, it's an alteration of the numeric value of the mass caused by non-potential interaction, because T represents directly this non-potential interaction beginning from Newton. That will be my little 3 or 4 minutes comments later on. And this allows us, as a concrete example, the synthesis of the neutron in the core of a star from a proton and electron has absolutely no solution, because the mass of the neutron is bigger than the sum of the mass of the proton and the electron. Schrödinger equation blows the solution. The solution is impossible. However, the moment we admit the contact non-interaction between the proton and the electron, calculation and experimental value implies immediately an iso-renormalization of the mass of the electron from 0.511 million electron volts to 1.25 million electron volts, under which, and here is the important point, under which the Schrödinger equation requires a physical solution. We know absolutely no other way. After working at the problem for decades, I know no other way, no other way to represent the most fundamental event in nature, which is the synthesis of the neutron in the core of star.
Okay.
Okay.
So we have defined iso addition and iso subtraction in this way. This was the first example. After we use the rule, we get for their iso addition to be this iso matrix, and for their iso subtraction to be this iso matrix. The defined properties have the following, the defined operations have the following properties. We take 3 iso matrix, then we have commutativity and associativity. The iso matrix, which is defined in this way, where in the diagonal participate the basic iso unit hat I, will be called iso unit iso matrix. This is the definition for this iso unit iso matrix, and using it we will deduct multiplication, iso determinant, iso inverse of iso matrix, and so on. So for an arbitrary element A hat F, which is belongs to our set with several iso units, and for one arbitrary iso matrix, we define the iso multiplication of this number with the iso matrix hat A in this way. For representation of the elements of this iso matrix is given in this way.
Excuse me again, question. And in the before slide, you are presenting ISO unit, ISO matrix. But the elements are all of them equal or are different in the diagonal?
They are equal because see here the different columns corresponds to different ISO spaces with different ISO units, but the actions between the elements of different ISO spaces with different ISO units corresponds to the new ISO space with ISO unit head T.
Then I can interpret this like the product of one ISO unit with one normal matrix unit. That right?
Yes, right.
Okay, thanks.
So we consider the following example. For the isotopic element head T, we take 2. For the isotopic element head T1, we take 4. For the isotopic element head T2, we take 3. And for the isotopic element head T3, we take 5. Consider the following real matrix. Its ISO lift using this ISO units is given in this way. And if we consider the ISO multiplication of the number 10 by this ISO matrix, we get this isometric matrix. Then as next example, we take for the isotopic element head T to be equal to 4, isotopic element head T1 to be equal to 1 over 3, and for the isotopic element head T2 to be 1 over 4. We consider two real matrices, A and B, and we will find this quantity. Firstly, their iso lift is given with these two iso matrices. This is head A and head B. Then firstly, we find the iso multiplication of the number 2 with the iso matrix head A, and the iso multiplication with the iso number 3 with the iso matrix head B is given with this iso matrix. Then the difference between the founded iso matrices is given with this iso matrix. So next example, we consider for the isotopic element head T to be equal to 2, head T1 to be equal to 2, head T2 to be equal to 3, and the fourth isotopic element head T3 to be equal to 4. Take two real matrices A and B, then we will find this quantity. For this M, firstly, we have to find the isolifts of the matrices A and B. The isolifts of the matrix A is the matrix head A, which is given with this matrix. And the isolift of the matrix B is this iso matrix. From here, we find firstly the iso multiplication of the number 3 and the isometrics head A, which is equal to this isometrics, and the iso multiplication of the number 4 with the isometrics head B is equal to this one. Then their difference is given with this isometrics. So some of the properties of the definite operation are the following. Consider two isomatrices head A and head B, two iso numbers A and B. Then for the iso multiplication, we have this property. For the distributivity law, we have this equation. And here we have, again, distributivity law, but when we have iso addition of the corresponding iso numbers. So now we move to the so-called isomultiplication of two iso matrices. Consider two iso matrices head A and head B with these entires. Then the isomultiplication of the isomatrices head A and head B is said to be the isometrics with these entires Cig, head Tg, where they are equal to this quantity. This is isomultiplication of two isomatrices. And as an example, we consider as the first isotopic element head T1 to be equal to 1 over 2, head T2 to be equal to 3, and this to be real matrices. Their isolifts is given for the first matrix with this matrix, and for the second matrix with this isomatrix. Then the isomultiplication of the above isometrics is this isometrics. Now we consider the isotopic element to be equal to 2, the first isotopic element to be equal to 1 over 2, the second isotopic element to be 1 over 3, and the first isotopic element to be 1 over 4. Take two real matrices, A and B, then their isolifts are given with the following isomatrices, head A, which has the following representation, and head B with the following representation. From here, using the given definition for isomultiplication, we find that their isomultiplication is this isovector. And as a fourth example, we consider for isotopic element head T to be equal to 3, head T1 to be equal to 1 over 4, head T2 to be equal to 2, and head T3 to be equal to 1 over 3. Take two real matrices, A and B, and we'll find their isomultiplication. For this end, firstly, we find their isolifts. These are the isomatrices head A and head B, respectively. Using the given definition for isomultiplication, we find the following isometrics. So isopower of an isometrics is defined in this way. This is the isopower. This is the power of isometrics. Here participate the isomultiplication. Here is the classical multiplication of the isomatrices. Now we will move to the definition for isodeterminant of isometrics. For a given isometrics, square isometrics head A, we define isodeterminant as follows. Isodeterminant of the isometrics head A is equal to this number. Here participate the isotopic element head T, and in the denominator the other isotopic elements. So if we take a matrix with two rows and two columns, then using the definition for isomultiplication, we find that the isodeterminant of this isomatrix head A is equal to this iso number. Here we have used the rule for the isomultiplication of the iso numbers, this iso number and this iso number, because this iso number belongs to different isospaces. In their multiplication, we use the general isotopic element head T minus the isomultiplication of the other above elements, which is equal to this element. And we get for this isodeterminant to be equal to this one. In this way, we show that if we use the rules for the isomultiplication, and we deduct the isodeterminant of a square isomatrix with two rows and two columns, then we get the same result as we have given this definition. When we put here n to be equal to 2, we get what we deducted here. So as first example, we take for the isotopic element head T to be equal to 2, head T1 to be equal to 1 over 3, and head T2 to be equal to 1 over 4. We take the real matrix A to be this matrix. Its isolift in for this isotopic elements is given with this isomatrix. The determinant of the real matrix A is equal to -7, but the isodeterminant of the corresponding isomatrix head A is equal to this number, -168. This number is different than this number. This next example, we take for the isotopic element head T to be equal to 2, head T1 to be equal to 2, and head T2 to be equal to 4. We take this real matrix. Its isolift is given with this, with this isomatrix. Then the determinant of the matrix A is equal to -8, but the isodeterminant of the corresponding isomatrix is equal to -2. Again, we get different numbers. As first example, we take for the isotopic element head T to be equal to 2, head T1 to be equal to 1 over 3, head T2 to be equal to 1 over 2. We consider this matrix A, which is given in this way, where X is a real number. We will solve the equation isodeterminant of the isomatrix A to be equal to 1. The isolift of the matrix A is the following isomatrix. The determinant of the matrix A is equal to 7x minus 10. From here, we find the isodeterminant of the isomatrix, which is equal to this number. And from here, we get the following equation, or we find this real number x to be equal to this number. So now we'll consider a square isomatrix with 3 rows and 3 columns. Again, if we follow the rules for isomultiplications, for its isodeterminant, we obtain the sum of the following numbers, this one, and this one, minus this number, and this number. From here, we get that isodeterminant of the isomatrix A is equal to this number. Again, we see that this number we can get when n is equal to 2 in the definition given for isodeterminant. So we can use both definition for square matrix with 2 rows and 2 columns and square matrix with 3 rows and 3 columns, both definitions as equivalent. As first example, for the case n is equal to 3, we take for the first isotopic element head T to be equal to 2, head T1 to be equal to 3, head T2 to be equal to 4, head T3 to be equal to 5. We take this real matrix. Its isolift is given with this isomatrix. We see different matrices. For the determinant of the matrix A, we get this number, 510. For the isodeterminant of the isomatrix head A, we get the number 34. These two numbers are different. As next example, we take for the isotopic element head T to be equal to 1 over 2, head T1 to be equal to 1 over 3, head T2 to be equal to 1 over 4, and head T3 to be equal to 1 over 5. We take this real matrix A. Its isolift is given with this isomatrix. Both matrices are different. For the determinant of the matrix A, we get this number. And for the isodeterminant of the isomatrix A, we get this number. Both numbers are different. In this case, we obtain that this isodeterminant of the isomatrix A is greater than the determinant of the matrix A. As next example, we take for the isotopic element head T to be equal to 1 over 5, head T1 to be equal to 1 over 4, head T2 to be equal to 1 over 3, head T3 to be equal to 1 over 2. For the real matrix, we get this matrix A, and its isolift is given with this matrix. For the determinant of the matrix A, we get this number, but the isodeterminant of the isomatrix A, we get this number. Again, we get different numbers. So now we will define what is iso inverse isometrics of given isometrics head A. We take a real matrix A, square real matrix A with n rows, which is non-singular. In other words, its determinant is different than 0. With Aij, we denote its cofactors. Then we define iso inverse isometrics of the isometrics A in this way. In this way, we define iso inverse isometrics. This is very different because here in the denominator participate the main isotopic element, and here participate the in the first row first isotopic element, second row second isotopic element, and so on in the last row the last isotopic element. Yes.
Tell what the capital T is compared to T1 is the T square, the T in T square. Could you please tell me? I'm sorry, it's not clear. I may have missed your definition.
Because see, now I will explain my definition. I give this definition so that using the rules for isomultiplication, we to get the iso unit isometrics.
No, but I do not know what the capital T in the square is. You see,
capital head T is the basic isotopic element. We have one isotopic element head T and n isotopic elements head T1, head T2, and so on, head Tn.
So head T is a matrix, is that correct?
Yes.
Okay, this answered my question. Okay.
So now the definition is given in this way, so that to get the iso unit isometrics. When I search the definition, what is iso inverse isometrics, I take arbitrary coefficient Cij. Then using the rules for the isomultiplication, I find that this iso elements has to be equal to this element, this one, this one, this one, and so on. So if we follow the rules for isomultiplications, for the element Cii, we get this element 1 over head T, which is the iso unit. And for the other elements, we get 0. Then this isomultiplication is the iso unit isometrics. If we consider the other isomultiplication, on the right is the iso inverse isometrics. Following again the rules for the isomultiplications, for the diagonal elements dii, we get again the iso unit elements. For the elements which are not on the diagonal, we get they're equal to 0. Then our definition for iso inverse isometrics of given isometrics is correct, because we get that the isomultiplication from the right and from the left with this iso inverse isometrics with the isometrics head A is equal to defined iso unit isometrics. It is difficult as definition, but this definition is very correct. As we see, yes.
Yes.
Yes, it is the elements of this isometrics are not standard here. This one. When we define isometrics, in the first row participate the all iso units head T1, head T2, head Tn. But here in the iso column participate these iso units. As Dr. Page asked, if it is possible to exchange the columns and rows, yes, it is possible. But when we define the iso inverse isometrics, this column has to be row. In other words, that transpose isometrics. So the definition is very correct. Now, as first example, we consider head T to be equal to 2, head T1 to be equal to 3, head T2 to be equal to 4, head T3 to be equal to 5. We take this matrix A, which is given in this way, we will find the iso inverse isometrics of the isometrics head A. The iso lift is given with this isometrics. Then we find for the determinant of the matrix A to be this number. Then the inverse matrix of the real matrix is this matrix. But the iso inverse isometrics of the corresponding isometrics is this matrix. This matrix, this one, is very different than this one. This is the classical case. This is the iso case. So as first example, we consider for the isotopic element head T to be equal to 1 over 2, head T1 to be equal to 1 over 3, head T2 to be equal to 1 over 4, and head T3 to be equal to 1 over 5. We take for a real matrix A to be this real matrix, and to find the iso inverse isometrics of the corresponding isometrics. The iso lift of the considered real matrix is this isometrics. The determinant of the considered real matrix is this number, and the inverse matrix of the given real matrix is this matrix. But the iso inverse isometrics of the considered isometrics is this isometrics. This isometrics is very different from this one. So as next example, we take the isotopic element head T to be equal to 2, head T1 to be equal to 3, head T2 to be equal to 2, head T3 to be equal to 3. And for the real matrix, we take this matrix, we'll find the iso inverse isometrics of the corresponding iso lift. So the iso lift of the matrix A is given with this isometrics. The determinant of the matrix A is equal to -3. And for the inverse matrix of the real matrix, we get this matrix. And the iso inverse isometrics of the considered isometrics is this isometrics. This isometrics is different than this one. As we saw that I have given a definition for isometrics. Then using the defined iso multiplications, which are originally defined by Professor Santilli and discussed in the previous lectures, we define what is iso multiplication, what is iso unit isometrics, and what is iso inverse isometrics. And we saw that all definitions are correct. Then the theory of the isometrices with different iso unit elements is built, and it's ready. Using this theory, we'll represent iso rotations and many other objects in Iso-Analytic isogeometry. So iso rotation. Now, we take an arbitrary iso point head P, which belongs to this iso space. an arbitrary iso vector, and with het L we denote an iso line, with iso direction iso vector, het V. We represent this iso vector in this way, using the defined iso trigonometric iso functions. Then for the corresponding iso direction iso vector, we get this representation. For the isonormal iso vector to the considered iso line, we get this representation and this one. Then the iso inner product of the iso direction iso vector het V and the isonormal iso vector is equal to 0. Then these vectors het N and het V are correct, and it is checked in this way. Then we consider the reflection of the iso point het X in this way, from where we find the difference between the reflection of the iso point het X and the iso point het P, and it has the following representation. Excuse me. The following representation. With het L O, we'll denote the iso line through the iso origin O. Then for the iso reflection with respect this line of the iso point het X, we get this representation. From here, we find a connection between the iso reflection with respect to the iso line het L and the iso reflection with respect to the iso line which passes through the iso origin O. In this way, from here, we'll compute what is the iso inner iso product of the vectors het X and the isonormal vector, and we find this representation. And for the iso reflection, we find the following representation in the language of matrices. Here is the matrix with 2 rows and 1 column. Here is the matrix, a matrix with 2 rows and 1 column. Again, here we use the defined in the beginning of this lecture, iso multiplication with iso number and iso matrix. So after we do some manipulation, we get this representation. From here, using the rules for the iso multiplication of iso matrices, here we get the following iso matrix. So in the classical case, we have only sinus and cosinus, but here in the iso case, for a isometrics iso representation of the iso reflection, there appear additional terms. Here in the first row, this is the additional term. Here het T1 is of power 1, het T2 is of power 2. Here on the second element on the diagonal, here the additional elements is het T1 square, het T2. The squares here and here are different. So this is the matrix representation of iso reflections. And these representations are very different than the classical, as we see. When het T1, het T2 are equal to 1, we get the classical, but this is the iso case. Again, after we use iso multiplication of iso matrices given in the beginning of this lecture, we can represent this isometrics in the following way. And in the end, the isometrics of the iso reflection is given with this isometrics. Very different than the classical. It was very difficult to deduct, but it is possible. So if we take two isolines head alpha and head beta through the isopoint head P, then the isometry head alpha after head omega head beta is called isorotation. When this isoline head alpha and head beta are isoperpendicular, then the isorotation is called iso half turn. So as example, we take head T to be equal to 2, head T1 to be equal to 1 over 2, head T2 to be equal to 1 over 3. We take the point X to be this point, the point P to be equal to this one, and the vectors V and W are these vectors respectively. The isolifts of the points X and P are the following isopoints at X, at P, and the isolifts of these vectors are these isovectors. We will find the isorotation of the isopoint at X about the isopoint at P. Firstly, we find the equation of the isoline head L, which is given with this equation. Next, we find the equation of the isoline head M, which is this equation. After this, we will find the corresponding isonormal isovectors of the isolines head L and head M. For the isonormal isovector of the first line head L, we have this isovector. For the isonormal isovector of the second line head M, we get this isovector. From here, we make some computations. Firstly, we find this difference between the isopoints head X and head P. Then we find this iso-inner product. From here, we find firstly the point head X1. Then we find the isoreflection of the isopoint head X1 with respect to the isoline head M. For this M, we find the iso-inner iso product between these two isovectors. From here, we compute using again the rules for isomultiplication with isovectors. We get this isovector. From here, again, using the rules for isomultiplications of isovectors, we get this isovector. Excuse me. And from here, we find that the isorotation, isopoint of the given point X is this isopoint. Here is given a picture. In green is given the isoline head L. In brown is given the isoline head M. Then we take in the red color the isopoint head X, and its isorotate is this isopoint given in blue. It is very different if we take the classical rotation. As next example, we take for the isotopic element head T to be equal to 1 over 2, head T1 to be equal to 2, head T2 to be equal to 3, two real points X and P, which will be these points, two real vectors V and W. Their isolifts are given with the following isopoints head X, head P, and the following isovectors head V, head W. We will find the isorotation isopoint of the isopoint head X. So firstly, we find the equation of the isoline head L, which is this equation. Then we find the equation of the isoline head M, which is this equation. After this, we'll search the isonormal isovectors of these isolines het L and het M. For these isonormal isovectors, we have this representation. And for the second isonormal isovector, we get this representation. From here, we find the isodifference between the isopoints het X and het P. Then we find the corresponding iso-inner isoproduct using our rules. From here, we find the isopoint het X1, which is this isopoint. Then we find the difference between the obtained isopoint and the given isopoint P. After this, we find this iso-inner product, which is equal to this one. And in the end, the rotation isopoint of the isopoint X about the isopoint P is this isopoint. In this figure here, in the green color is given the isoline het L, in the brown color is given the isoline het M, in the red color is the given isopoint, and in the blue color is given its isorotation isopoint. If we take but the classical rotation, we cannot get as a result this point. Then the results in the classical and iso cases are different. And as next example, we take for the isotopic element het T to be equal to 2, het T1 to be equal to 1 over 2, het T2 to be equal to 3. We take two real points X and P, two real vectors V and W. Their isolifts are the isopoints het X, het P, and isovectors het V, het W. We'll find the isorotation isopoint of the isopoint X about the isopoint P. Firstly, the equation of the isoline het L is given in this way. The equation of the isoline het M is given in this way. Then we will find the isonormal isovectors of these isolines het L and het M. And these isovectors are given, the first one in this way, and the second one is given in this way. So firstly, the isoreflection of the isopoint at X with respect to the isoline L, het L, is given with the isopoint het X1, and we get this isopoint after we do all computation for the corresponding iso inner product and iso multiplications between the iso number and iso vector. And after we continue the computations, we see that the iso rotation isopoint of the point at isopoint at X about the isopoint at P is this isopoint. In the next picture, here in the green color is given the isoline het L. In the brown color is given the isoline het M. This is the given isopoint X, and here is the is this isorotation. Again, we cannot get if we use the classical case. So now if we suppose that both lines het L and het M are isoperpendicular, we will find a suitable representation of iso-half isoterm of a given isopoint. In the case when both isolines are isoperpendicular, for the isonormal isovectors, we have for the first one this representation, for the second one this one. These two isovectors are iso-unit vectors. Their isolength is equal to the iso-unit. These two isonormal isovectors are isoperpendicular. And using our formula for isorotation, but now in the case when both isolines are isoperpendicular, we get that after we make in the task all computations and some manipulations in these computations, we get that the iso-half iso-term can be represented with this formula. See, in the end of the formula for iso-half iso-term participate only the basic isotopic element head T. But in the representation of the iso rotation, in the representations participates and the iso units element head T1, head T2, and the basic isotopic element head T, which is given head L, head omega, iso rotations, the formula, yes. But for the iso-half iso-term, we have only the basic iso unit head T. We have here this. So I will give some examples when the isotopic element head T is equal to 2, head T1 is equal to 3, head T2 is equal to 4, two real points X and P, then their isolifts are given with these iso points, and the iso-half half iso-term iso point is this point. It is very different than the classical case. If we take for the isotopic element head T to be equal to 1 over 2, head T1 to be equal to 3, head T2 to be equal to 2, two real points X and P, then their isolifts is given in this way, and the iso-half iso-term is given with this iso point. And as a last example, we take for the isotopic element head T to be equal to 2, head T1 to be equal to 4, head T2 to be equal to 1 over 2, two real points X and P. Their isolifts are given with these iso points, and the iso-half iso-term of the iso point X with respect to the iso point P is given with this iso point. So, and in the end, I will give a definition for isogrid isoreflections. An isogrid isoreflection is defined to be an isoreflection followed by an isotranslation along the isomirror. So, if we take for the iso line to be this iso line, then for the representation of an isogrid isoreflection, we get the following formula, this one. And only one example, when the isotopic element head T to be equal to 2, head T1 to be equal to 3, head T2 to be equal to 4, two real points X and P, which will be these points, and one vector V. Their isolifts are these iso points and this iso vector. For the equation of the iso line head L, we get this equation. For its isonormal iso vector, we get this representation. For the isogrid isoreflection iso point, we get this iso point. Here is given the line head L in green. Here is the point at X, and here is the point, the isogrid isoreflection point. And the last definition, that an isometry that is product of a finite number of isoreflection is said to be an isomotion. So in this lecture, we have defined what is isometrics, the basic operations with isomatrices, iso-addition, iso subtraction. Then we define iso-multiplication of isonumber and isometrics, and iso-multiplication of isomatrices. So if we consider an isometrics, an isovector as an isometrics, then above definitions are compatible. then all definitions given here are correct. Then we have defined what is iso-inverse isometrics. Then using the given definition for isomultiplications of iso numbers and isomatrices, we find that the isomultiplication of the isomatrix and its iso-inverse is the iso-unit isometrics. Then again, we have a correct definition for iso-inverse isometrics, and using isomatrices, we have given the isometrics of isoreflection and the isometrics of isorotation, isometrics of isoglit isoreflection, and we have given the isometrics of iso-half isoterm. Okay, thank you.
Okay, thank you.
Okay, thank you.
Well, it's a lot to absorb at one point, and my first comment would be just that although you've given a lot of numerical examples and a few pictures or graphs, I have very so far sort of an unclear intuition as to how an isorotation and isoreflection differs from the usual notions, the common notions.
Yes, see, isoreflection, for the isoreflection isometrics, we have the following isometrics. Let me find. So this one.
Maybe to clarify my
See,
question.
See, yes, for the isometrics of isoreflection, we have this representation. Here participate the buff iso units, and the basic iso unit had t. In the classical case, we have here 1 minus 2 square sinus of theta. Here we have 1. And here in the classical case, we have sinus 2 theta. But here participate the iso units and isotopic elements in this way. Above definitions are different because in the classical definition for reflection, we have not this term, but here it is a pure additional term. This is for isoreflection. For the isorotation,
but I see formally the difference as you're pointing them out, but I don't have a physical intuition as to what this geometry is describing. Like a physical example would be if I stand in front of a mirror and I wave my left hand, I see the reflection waving its right hand, right? So if I were to stand in front of an iso mirror of some sort, how does that differ? Like, how does it?
May I try to make a comment that's important, as usual, very important question, very intriguing. The best way that I know is that all isotopic theory, in particular the isomathematics, has a dual interpretation. While the conventional mathematics is only one period, rotation in conventional mathematics is one idea period. In isomathematics, the way this was developed, there are two different interpretations. First, there is the interpretation of what is an isorotation, but here is the question should be completed. What is an isorotation on an isospace over an isofield? And the answer is identical to the conventional rotation on a conventional space on a conventional field, by the very, very notion of isotopy. So what you see, this incredible complexity that Dr. Georgiev correctly indicated to illustrate what we are talking about, is we are talking about the projection of the isorotation in a conventional space. There you see all this complexity. But however, the physics is in the abstract formulation on an isospace over an isofield. At least I beg you, I'm not pretending to answer your question. No. I'm telling you the way I handle this complex. I know this because we hit we had a big problem when we work on isorelativity. So the question was, what is the maximal causal speed for an isorelativity? And the answer, since on the isotropy, everything has to be preserved. So the answer was precisely what I told you, namely that if you look at an Iso-Minkowski space, it's relatively simple to prove that the maximal causal speed is a conventional speed of light in vacuum. However, here's the physics. When you project Iso-Minkowski space of our atmosphere, for instance, in a conventional Minkowski space, the speed of light is c divided by the index of refraction. So you see the difference appear in the projection. To the best of my knowledge, sorry, something went wrong.
I like it too much the phrase of Professor Page, like ISO mirror. No? Then I think that with this formalization, we are trying to transform the usual view of the phenomena to another view. And in this way, I liked too much to the idea of ISO theory, like a mapping of the standard mathematics. Standard real numbers, standard vectors, standard modules, and so on. Then if we think in this like mapping, then the question about what is the meaning of reflection or rotation or something like this, because of course in the numerical examples that we are that the Professor Georgiev have presented to us, we find many differences, and then we can see how one matrix in the standard mathematics is look in the ISO mathematics. We get the difference, but what is the meaning of rotation there? Or what is the meaning of reflection or geometry there? And I think this is the principal question here. I don't know if formally, but I think that it is a correct view. We can think about ISO numbers like one mapping of operators, of numbers, of fields, and so on. Then I think that it is important to clarify this formal aspect in the way that we can get a more intuition about the meaning of these ISO numbers. Thanks.
Yes, in my case, I have deducted all things in mathematical viewpoint. I have not physical interpretation. I'm a mathematician. I sit down to see how these ISO numbers reflect in ISO function, in different geometrical objects, in algebra, and so on. Maybe Professor Santilli will give more explanation. What is the this is the mathematical meaning of this terms: iso-rotation, iso-reflection, iso-mirror, and so on. Maybe Professor Santilli will give more comments regarding their physical applications and meaning.
Thank you.
Okay.
We can do a very concrete example by considering our atmosphere. Again, if you think about the empty space, then there is I think isomathematics is applicable, and if it is applicable, it's marginal. So we're talking about application within physical media. So consider, for instance, our atmosphere. In the atmosphere, the speed of light in our atmosphere is not the speed of light in vacuum. This is now accepted by the majority. But the speed of light divided by the index of refraction. Index of refraction is a measure of the density. So here you see the index of refraction is in the formulation that you have seen of Dr. Georgiev, will be T4. In a 4-dimensional space, the index of refraction will be the isotopic element T4. But then you look at the space component, then the atmosphere is inhomogeneous and anisotropic. So you need 3 different quantities to represent all 3 of them, because they have to represent the variation, the local variation of the density with the elevation and the anisotropy and so on. So in our language, we have N1, N2, N3, and N4 in the physical application. The lecture that you have heard today will be T1, T2, T3, and T4. And you will see the concrete physical representation of each of with numerical value for each of them, or function. In this case will be all function, because the index of refraction depends on the density and the temperature, but primarily on the density and the same so on. So let's go now to the question. So this is as an illustration of what isotopic elements are. Then let's go to the very important question, and I'm really grateful that you posed this question, because those questions can help us to think deeper and deeper, and usually end up with new formulation. But the question is, let's do the case of rotation. Well, we have the rotation in our atmosphere is essentially suppose you have an object that rotates in our atmosphere, and you do the isotopic representation. At the an Minkowski space is a conventional. There is no by assumption. And if you have difference between the conventional formulation and the isotopic formulation on isospace over isosphere, in our view, I may be wrong, but in our view, we suspect that the isotopy is not correct. So at the isotopic level is complex. So your question is reduced to what is the meaning of the projection of this abstract rotation, this abstract space, into our physical space-time. This, I believe, is my kind of reformulation. And the answer of this it is that it's not. Of course, you continue the rotation, but jointly you can have an hyperbolic motion in the atmosphere. In other words, the sphere was not a perfect sphere, so therefore created some resistance in the air. So you have to imagine a kind of an oblong object that starts to rotate, but then instantly jumps on one side, on the other, like a UFO, literally like a UFO, jumping from one side to the other, because there is a representation of all the effect of the resistance of the medium on the object that you consider. The primary assumption being that you consider the object being point-like. Everything I said makes absolutely no sense. Point-like object cannot sense any resistance. So everything that I mentioned applies for an extended object, an extended, not perfectly spherical, oblong. Then you have to take necessarily into account the resistance. And that's what that's why the isotopic element represents the distance. So the problem, so in an iso-Minkowski space over an isofield, you have a perfect conventional simple rotation. But then you look at the projection on a conventional Minkowski, you have absolutely crazy, totally crazy behavior of the object. The object remains what it is because it's assumed to be rigid, extended, non-spherical, dense, but not rigid. But rigid in first approximation, otherwise becomes so complicated that but you have seen the complication of Dr. Georgiev. So under this assumption that ellipsoid, they have an absolutely crazy motion in our atmosphere, depends on initial conditions and so on. So the answer is that in physical application, yes, we do have a very concrete answer to your important question. Mathematically, however, I do not know. Mathematically, I do not know. Dr. Cruz, you also had an important point that I would like to express my appreciation and support, namely the use of a map. That is indeed, the isotopy should be interpreted as a map. I'm not only one. Dr. Nunes and Conformina made their own interpretation of isotopy via what they call topism. Dr. Georgiev can elaborate because he had a conference with them that I could not attend, and they presented their view. But if you are interested, we can get the information.
Dr. Sobchak, your audio is not, I cannot hear your audio. No, still not.
May I ask what time it is, Dr. Page?
It's approximately 20, well, it's 1 hour and 20 minutes since the beginning of our, so the time for me locally is 23 minutes after 1 p.m.
Well, we have time. My presentation is only 4 or 5 minutes at the most, something like that. So we have time to discuss the subject.
Okay. Dr. Sobchak seems to be having some audio difficulties. He seems to be speaking, but I don't hear him speaking.
Maybe your microphone level is.
No, I don't hear him either. I don't hear him at all. Well, let's take the time. Dr. Page, I think you had in your comment during Dr. Georgiev lecture, you had another of the many important points that let me see if I understood correctly. Essentially, you raised the issue: what is a matrix in which the elements are matrix? The reason being because the definition of a matrix is that an isomatrix is a matrix with iso number as element. But you have seen in our physical application that the iso unit is a matrix. Iso number is a number multiplied by a matrix, so that's why you end up with a matrix inside matrix. But let me tell you that let me tell you the difference between our physical theory and Dr. Georgiev. In our physical theory, of course we know that this is it's very complicated idea to have a matrix whose element are matrix. And but the point, we don't care much. The reason being, if you look at all the calculations, at the end the isometrics disappears. So we look at we consider this just a formal aspect, and we go to the end. I remember that the final results are an iso number isotopically multiplied by an iso state. This process, the iso unit disappears, you end up with ordinary conventional number. That's in physics. However, I want to bring your attention the Dr. Georgiev presentation. Basically, Dr. Georgiev, precisely to eliminate this point, however, in my interpretation of Dr. Georgiev, I hope to be correct, but in order to eliminate this issue, Dr. Georgiev considered the isotopic element the product. Isotopic in isometrics in n dimension is reduced to a direct product of n isotopic elements. And that's why you see in the definition of Dr. Georgiev's definition of isometrics, you don't see the iso unit, but you see the individual isotopic element. By therefore eliminating this, resolving the correct issue that occurs at you raised regarding the question, what is a matrix with elements are matrix? Does it make sense, or I don't know?
No, I don't have any problem with the idea of a matrix whose elements are matrices. I mean, since a matrix is a ring, and we only require that the elements of a matrix be scalars. So scalars come from whatever ring you like to choose.
Okay,
so that
yeah,
ring could be
can you
another
hear me now, by the way?
Okay, now we can
Yes.
hear you.
Okay, you can hear me now, right?
Yes, that's great.
Okay, yeah, I was going to comment related to what you're commenting on, namely the T and the T1 and T2. It's only the T that really defines the multiplication between matrices, whereas the T1 and T2 are for the different dimensions, if I'm not mistaken, how it's being done. So really the T is used globally, you might say, whereas the T1 and T2 are for each separate dimension that the matrix is in. Is that correct?
Dr. George,
Yes, yes.
I think it's
So,
only equal to the column dimension, right?
see,
Yeah, so for example, we set T1 equal to T2 equal to 1, then we only use the matrix T, which is a global.
yes. It is possible in the case when these isotopic elements get T1, get T2, and so on, get Tn to be equal to 1. But the basic isotopic element, this one, get T, to be different than 1. So when I try to define what is isometrics, firstly, I observe that it is impossible to take the elements in a random way, because see, it is impossible here this element to be from head T1, here to appear as fourth element again from head T1, because we have to then we have to obtain a strong theory where we have iso multiplication of iso matrices, iso determinant, and iso inverse. Using this, what will be iso inverse, so that to get the basic isotopic element when we iso multiply between two above iso matrices, I observe that these elements has to be ordered in this way. It is possible to transpose this matrix. This is no problem, but these elements, they are not random. Here is head T1, head T2, and so on, head Tn. It is impossible to have one after one the same isotopic element. So that to build a mathematical theory where to work all things, iso-determinant, iso-inverse, isometrics, and so on. In one example, I have given what is equation, because in many cases we go to some equations as here. If we consider this element to be from head T2, we cannot apply the theory. But this element we take from head T1, this from head T2. Isometrics not in random way. We have to order using the isotopic elements. Also, A particular case of isometrics is an isovector. We have a theory for isovectors, as in the previous lectures. Also, the theory for the isovectors coincide with the theory of Santilli. Then, to define isometrics and so on, isodeterminant and isoinverse, we have to follow my way. Okay.
Yeah, okay, so thank you. So yeah, T plays quite a different role than the TIs for each separate dimension.
Yes, here.
It's a formulation different than what we use in physics. In physics,
Yes, different. Yes, different. But if we contact, we can try to find some joint representation, so that this to be in physical and mathematical. But in mathematical view of point, to define isodeterminant and isoinverse in this way only. I have tried many possibilities.
well, in Dr. Georgiev, in our formulation, this is in our formulation as an isometrics. All the T's will be replaced by the matrix, which is the iso unit. So,
yes, it is possible. It is possible. Now in this lecture we see scalar, but it is possible if we replace this head T1 to be isometrics. This is not problem.
In our case, there are one and only one, and which is given by the iso unit, which is the inverse of the capital T used in the isotopic product of matrices. That was the point of Dr. Subject, the correct point by Dr. Chopsik. So is one of the reasons why the formulation of isometric is an n-dimensional isometric. When each number, ordinary number, is multiplied by the iso unit, which is n-dimensional. And then in this case, if you look at volume 1 of Elements of Hadronic Mechanics, the definition of the iso inverse, iso determinant is much, much simpler than in your case. So, it's a different formula. I want to bring to your attention that it's a different formulation. It's perfect, it's beautiful, and please don't misunderstand me. But it's a different one. That's why in physics we use we only use the iso unit multiplying each and every element. Iso unit as a matrix, because it simplifies everything
Yes, I understand.
In that case, Dr. Santilli, do you still have this distinction between, say, T with a subscript and T without the subscript?
The T with subscript do not exist in physical formulation. No, but however, I shall indicate that that perhaps I'm not a mathematician, but perhaps Dr. Georgiev's formulation is mathematically more accurate than ours. Mathematically, but physically, physics is done with absolute minimum use of mathematics. Complex mathematics is used if and only where really necessary. So that's why we use only one entity, which is either the isotopic element as an n-dimensional matrix. In the case of Minkowski space, it's 4-dimensional. The diagonal elements are n1 square, n2 square, etc., etc. And we use so an isometrics is a matrix was element given by ordinary number multiplied by that 4x4 diagonal matrix. Then the calculations are very easy. But the question persists mathematically as to whether the Georgiev formulation is more accurate of decomposed the product of 4 individual units, 4 individual isotopic elements. This means decomposing the isofield in the direct product of 4 different isofields, one per each degree of freedom, if you want. So the question is which is a mathematical issue, not a physical issue. We prefer the unified definition with one single matrix per, because that's in the inverse of the isotopic product. Everything is very simple and linear. But the issue persists as to whether this decomposition is more appropriate. I will not know the answer.
But in Dr. Georgiev's formalism, if we were to make T1 equal to T2 equal to 1, this might still be, for example, a isomatrix, even though T1 and T2 are both equal to 1, but the elements of the isomatrix would then be ordinary numbers, correct?
Yes, yes, but it is possible these numbers to be considered as metrics.
Oh,
Okay.
yes, but in Dr. Santilli, maybe just for clarification to understand what you meant, Dr. Santilli. So you are still talking about an isomatrix of iso numbers, correct?
Absolutely.
Yes.
Yes. So in that case, the T1 and T2 cannot both be equal to 1. They might be equal to each other, but they still have to be something other than 1.
Sorry, the page. The question is inapplicable because T1 and T2 do not exist in our formulation. Period. They don't exist at all. The only thing,
But the only way that iso numbers exist in Dr. Georgiev's formulation is if T1 and T2 are not equal to 1.
that's a separate issue. There's a different formulation than ours.
Yes. See, when we were in Greece with Professor Santilli, Rhodos, then Professor Santilli proposed to be considered isovectors and isomatrices with different iso units. And now you see the result. Because so far, they're considered only one isotopic element. Now the isotopic elements are different. Okay? This was for different isotopics elements as head T1, head T2, and so on. This was general proposition and question by Professor Santilli in Rhodos,
Yes,
in Greece.
remember
Yes.
this.
Yes, and then I say that this is a very difficult because we obtain very complicated computations, as we see.
Yeah, I remember discussion was the proposal came out of our collegial discussion on nuclear physics, in which we use different nuclei that we want to fuse. We want to study nuclear fusion of two different nuclei into a third nucleus. And of course, the isotopic element of the two nuclei must be the different among themselves because they are different nuclei. And so therefore you go out, that is, and you end up precisely with your formulation. Dr. Georgiev, thank you for remembering me this nice conversation in Greece. It was very nice.
Yes, yes, yes.
I'd like to just come back to Bill's question. Suppose we choose T1 and T2 equal to 1 and let T be whatever you want it to be, and then ask the same question, what would a mirror reflection look like in this case when you simplify it to T1 and T2 equal to 1, but T is, and it's
Different
much easier to say what reflection would look like then.
Yes, now I will answer directly.
But this is a conceptual answer, Dr. Georgiev. But there is no need of equation. Let's consider the three-dimensional, because they look for concept. Let's consider a three-dimensional space. Then the subject, your point of putting T1 and T2 equal to 1 is very, very valid. Yes, indeed. What does it mean? That you have reflection only in one of the three-dimensional reference frame. In this case, the reflection is elementary. But this is, however, I have to insist in Dr. Georgiev formulation. If you go to what we use in physics, a different issue. In this case, you have a matrix, which is singular, because it's singular in the sense that the determinant is null, because the diagonal element will be 1, 1, and 0. So this is to illustrate the inequivalence of Dr. Georgiev formulation with ours. However, there is one point I would like to emphasize emphatically in my Italian language. Namely, I did this, check it out in detail. Dr. Georgiev formulation is indeed 100% bona fide isotopy. It's mathematics, it's 100% bona fide isomathematics because it verifies all axioms of basic axiom of isomathematics. Basically, what we're discussing is the point that came out of my own lecture on the Iso-Differential Calculus. I learned at you that there is this was the introduction precisely to the Georgiev lecture. Remember my point when I introduced the axiom of the Iso-Differential. I said, remember, we physicists have selected the simplest possible solution, and I show it to you. However, keep in mind that there exists a number of other inequivalent solutions that will be presented by Dr. Georgiev, and that's precisely what we are witnessing.
But I still would like to hear the sort of formal answer that Dr. Georgiev would give to Dr. Subject's question.
So when head T1 is equal to head T2 is equal to 1, for instance, for the isodeterminant of this isometrics, we get only head T multiplied by the determinant of A. Only one multiplication. When we have,
basically.
yes, when we have iso inverse, then this head T1 is equal to 1, head T2 is equal to 1, and so on. Then we get that the iso inverse matrix of the isometrics head A is 1 over head T square multiplied by the inverse matrix of the matrix A.
But the subject, I apologize, I was wrong in my statement because I assumed T1 equal to 0, T2 equal to 0, then and only then went up with singular iso unit. No, your case, I apologize, your case, it was for T1 equal to 1 and T2 equal to 1, and then T3 not any non-zero number. Then in this case, it may well be that Dr. Georgiev formulation is fully equivalent to our. I have not studied the case of the equivalence, but it may well be that the two formulations are equivalent because the isotopic element is the same. Because in Dr. Georgiev too, the isotopic element will be a three-dimensional matrix with a diagonal element 1, 1, and then T3, exactly as it is in our formulation. So I apologize, I was mistaken in the interpretation of your.
Excuse me, but I think that in my view, the meaning of the ISO unit is one way of representing one that there is not isotropy in the space. There is not isotropy in the space. And if all the elements are equal, then we recover isotropy.
Very, very true. But not necessarily.
Yeah, and whatever n dimension you want, whatever n dimension you want.
This is my little presentation on the ISO unit, which would like to address this issue. But you are absolutely correct. When you have when the ISO unit reduced to the conventional unit, all ISO theory recovers uniquely and identically the original conventional theory, including mathematics, is recovered uniquely and identically.
I think Dr. Georgiev still has not yet shown the ISO reflection in the case that Dr. Subject requested.
And is
You're basically following your request, actually.
Yes.
So
three-dimensional.
Iso reflection is given in this way. Here. This minus this. And here participate these isotopic elements, head T1, head T2. This is the
But we
iso
don't-
reflection of the point of the iso point at X.
Okay,
The
so,
iso-
so from this formula, we see that there is no hat T without a subscript.
Yes, because here we operate this iso point. We can this is iso vector, and then we operate as iso vectors. But head T is appear here, here, and here. It is
Oh, and the
written.
cross product.
Yes, here is head T, because in this, as it is written, here is iso multiplication. After we write the full form of this iso multiplication, here is appear head T. Okay, then we have head T1, head T2, and head T. This head T, the general basic element, comes from this iso multiplication. After we apply the rules for the iso multiplication given by Santilli, we get this. In this representation, we have both head T1, head T2, and head T. Then everything is okay.
So if we set the T1, T2 equal to 1,
That's what
Yes.
we'll have some difference.
well,
When they're equal to 1, then this vector will be multiplied, the classical vector will be multiplied by this isotopic element head T. This will be the, yes, when the buff elements head T1 and head T2 are equal to 1, then this matrix will be multiplied, the classical matrix will be multiplied by this isotopic element.
Okay, so what does that do to the reflection is the question then? By multiplying that second term by T. How would that change
that's what I'm-
left and right or whatever?
Because we use the rules for iso multiplication. And this is the representation after we apply the iso multiplication. And here is given this isotopic
So we
element.
should be able to get a picture though of a reflection.
A picture is given here for a private case. See, we take the green line. After we make iso reflection from of the red point here, its iso reflection is this one.
Yes.
It is not in the class, because in the classical case, if we take a reflection, we get the point somewhere here. Here the classical reflection, but the iso reflection is obtained here.
Would that be
And-
true if
and
T1 and
if-
T2 are equal to 1?
May I comment?
Okay, yes, I understand. For the next lecture, I will prepare examples here to be written, head T1 to be equal to head T2 to be equal to 1, and head T to be some number. And then
Yes.
we will see the difference, okay? And then in the picture will be shown the classical reflection and the iso reflection when these isotopic elements are equal to 1. Okay, I will prepare.
May I ask the question, the important question? Dr. Sadzik indicates consider a three-dimensional Euclidean, okay, conventional, and consider only one of the axes, for instance, the x. Okay, then we know what the reflection is. The reflection, the inversion, basically the axis remain on itself, only the plus and minus are exchanged. Okay, now you consider Dr. Georgiev equation. So for the case T1 equal to T2 equal to 1. Then on iso space over iso field, the iso the iso coordinate is exactly the same. It's inverted over itself, because at the isotopic level, you see nothing new by very notion of isotope. However, when you do the projection of this abstract representation in the old conventional Euclidean space, that's the projection. However, then not only you have an inversion, but the angle of the x-axis with respect to the other is arbitrary. It depends on the value of the T3. So you have to see that you automatically end up with a rotation in a way, rotation, however, in different space. So it depends on the numerical value of the T3 to see what is the angle between the projection of the iso axis x with respect to conventional x, y, and z. But there's nothing strange. Nothing strange. It's just in addition to inversion, you have additional other components, but there's nothing strange.
Yeah, one reason I like my so-called geometric algebra approach is because you get away from using matrices. You don't have to use matrices all the time. And of course, with that approach, I only use T. So I'd like to talk sometime about that as a special example, which really should be equivalent to with T1, T2 both equal to 1. So it might be valuable to because of the geometric interpretation that's available with the geometric approach.
Algebra. Okay. For the next lecture, all computations, in all computations, I will give in the private case when these isotopic elements are equal to 1. And we will see what is the difference. Because I know now I can explain only by words. But in the next lecture, we will see this formula is for the case head T1, head T2 is equal to 1. This formula is for the general case. Okay? And then we will see if there is an equivalence with the physical definition by Santilli, and if there is with this mathematical equivalence. Okay?
Okay, great. I think our seminar has gone on for a long time again. We have still the proposal, at least we've been discussing the possibility that Dr. Sobczak might wish to make a presentation. Garrett, do you have an idea as to when that would be best for you?
Well, I can do it anytime. Maybe, like I say, I could just give an example. Instead of, okay, so we'll hear from our speaker now, Dr. Georgiev, with T1 and T2 equal to 1, but I'd like to show actually exactly what it means in geometric algebra directly without using matrices. I don't like to use matrices. So I could maybe take 15 minutes and show that very quickly. I don't think these numerical examples really give any insight. Just seeing a bunch of numbers doesn't really help. It's the formulas that are important, not the numbers. The numbers just, it doesn't mean anything really. You don't get any insight from the numbers on the example. But
usually I think of the examples, or numeric examples are good at proving something false, but not, so they are good to do such calculations as counter examples, for example. But
just numbers just doesn't mean anything to look at these numbers really, except for this proof that you're talking about.
But in any case, we should clarify perhaps our schedule over the next while. It might be, one possible proposal would be that after now we've had sort of 3 lectures in a row, plus some background discussion, perhaps it would be reasonable to schedule a meeting specifically about, focused on discussing some of these various issues. There were questions that were raised by Dr. Sobczak, and I had a couple as well. sort of after Dr. Santilli's lecture. And perhaps it would be good to collect those questions and deal with those questions during our meeting. And this question also about examples, both from geometric algebra and from simplified versions of what Dr. Georgiev is showing us. Maybe we should collect that to just one meeting and focus on questions and discussions before continuing on our next series, like more formal presentations.
That sounds like a good me.
Okay, and perhaps as part of that, Dr. Subchik, you might wish to sort of review with us the document that you've drafted so far, just so we.
Yeah, I think I can just what I can clarify my formulas a little bit to agree with what Dr. Santilli and Dr. Georgiev notation, so it'll be much clearer exactly connections between the two.
Okay.
I don't really want to change what we're using, but I like to keep things as simple as possible and not have all these numbers all over the place all the time.
Sure.
Okay, so I propose for the next lecture to be prepared slides with all things so far, with both cases. First case, head Q1, head T2 is equal to 1, and second case, the general case. All things which we saw so far.
Well,
Okay,
really, just the formulas. We don't need the numbers. It doesn't really do any good to look at these numbers, except, so just give the formulas and then they should reduce them automatically without, the numbers just don't really give any insight at all.
Yes.
Or maybe just a few very selected examples, where.
Okay.
Just so we get an understanding of the technique, something like that. I
will
do have
prepare.
one other comment, and that is I personally have obligation for next Wednesday, that conflicts with our usual schedule. So the meeting could definitely go ahead if although I won't be able to be present in person, I would definitely be sure that we have a recording that I could view later, and or alternatively,
maybe next week we could exchange emails about questions and all that, and then not really meet formally, but just with email, either with everybody. We're 5 people in the group here, so back and forth, and then it might make more sense than to go from there.
And then to schedule the next seminar then in 2 weeks' time?
Yeah, that's what I would suggest, really.
That suits me very well, but
it's nice to keep all together.
So
I think that in 2 weeks is okay.
Yeah, there's another matter too. We have papers to review for the memorial journal as well.
That's correct.
So that's going to take time as well. So it would probably.
Yes, another reason why it would be convenient for me as well. Okay, all right. Well, I'll confirm that by email then, and we should continue our discussions. I encourage you to exchange emails. We have been doing that already a little bit, but with Dr. Subchik's paper, and I think that's been very useful for me. Thank you very much, Dr. Subchik.
You've helped me too. I think really that the latest definite. I'll talk about it in an email.
Okay, great. All right then. I think we should say goodbye for today and exchange emails over the next 2 weeks, and to meet again in 2 weeks' time.
Okay.
Okay.
Goodbye for now.
Goodbye.
Bye.
Okay, bye. Thank you.